What happens to the other x?
Yeah, sorry, I didn't finish it here.
No, not that one.
Oh, okay. This one here.
The one on the top. Like, no, that's the same. To the right,
Okay,
and then the x on the top, on the numerator.
this one here.
Yeah.
Oh, so I cleaned it up here. I made it x to the first power over x to the 1/2, which is the same thing as
Oh, okay.
x to the 1 times x to the negative 1/2. So I skipped a step there. Subtract exponents, 1 minus 1/2 is 1/2. Okay. Okay, questions with 5. 6 is the same way. We can merge all the y's into one variable with one exponent. We can bring it up to the top and just rely on power rule there. Okay, so 1 plus 1/2 is 3/2. But the y's are together, which is good, but this y is still a little bit out of place. We want to push that up to the top. Now it's in the perfect place for us to apply power rule, right? No radicals, no variable in the denominator, no multiple y's that are multiplied together, no parentheses to worry about. Okay. Questions with 6? Yeah.
So how's the integral like related to, like, how is it like equal to the summation thing? Like, it just looks so different.
Yeah, the process is very different. But let's say I had bounds involved, which we're going to talk about second half of class. If I were to evaluate the bounds by plugging it into this expression, my results will match the area definition that I did in the past.
Yeah, but like how? Like,
That I will have to kind of give more information to you later. Yeah. So right now, we went through that area definition because that is more visually helpful in seeing that helping us see the area creation of it. But I guess the short answer is that because derivatives involves power rule for that we went through. And so if we undo that power rule process, then we're basically multiplying, right? If we're multiplying, go with that multiplication process, then if we undo slope, then we're getting area. So that's why this also works for finding area under the graph. Okay, number 7. This looks messy, but what do you notice about the denominator here? There's only what? There's only one term, so this is not, we do not have to treat this like one messy fraction. We can split this up into as many parts as we need to, and then handle them individually, right? This is not one messy problem. This is probably multiple smaller problems, right? So we don't want to do any sort of, right, there's no quotient rule for antiderivatives. This is simply a power rule problem, but it does require a lot of cleanup. So I'm going to FOIL out that 1 minus x squared. I'm going to distribute that 3 root x through. I'm going to split up into individual fractions. clean up each individual fraction, make sure that every term is ready for power rule, and then we do power rule for all the terms individually. Now, you may be cleaning this up a little in a different order than me, which is fine. So as long as we're following that, we're not breaking any algebraic rules, you can do them in a different order. I'm going to skip a step here. I'm going to subtract the exponents. 1/2 minus 1/3, that's 3/6 minus 2/6, which is 1/6. Three halves minus 1/3. That's 9/6 minus 2/6. Let me see. 3 times. Sorry, 9/6 minus 2/6 is 7/6. Five halves minus 1/3. (15/6) minus 2/6 is 13/6. Okay, so now this is all nice and clean. Every term is ready for power rule. I resolved the denominator. I got rid of all the parentheses. And now power rule for each term. So we add 1 to the exponents. 1/6 plus 6/6 is 7/6. 7/6 plus 6/6 is 13/6. 13/6 plus 6/6 is 19/6. Flip all the denominator fractions up as reciprocals. So 3 times 6/7, 6 times 6/13, and 3 times 6/19. Okay, any questions so far? So we see we're going to be learning all these new antiderivative integral rules. But the good thing to know is that we kind of know them already because we're just undoing the derivative rules that we learned in the past. So power rule, we saw that, right? We're basically inverting the operations to get to the power rule for antiderivatives. So this is going to hold especially true for trig derivative or trig integral rules. Okay. So We do need to know these trig integral rules, but I don't want you to memorize them. I don't have them memorized. I lean on the derivative rules that I memorized and use those to help me get to the integral rules. Okay. So, and that just makes it a little bit easier, I feel, because if you can have the trig derivative rules spelled out in front of you, then it acts as a derivative rule and it acts as integral rules if you just know how to read it backwards. All right. So let's review the trig derivative rules, right? This is the way I like to line them up. I like to line them up with the C's in alphabetical order, and then sine, tangent, and secant, because I know that these are similar, and these are similar. Okay, so sine's derivative is cosine of u times u prime. Tangent's derivative is secant squared u times u prime. Secant's derivative is secant u tangent u times u prime. We know that cosine, cotangent, cosecant, they all have negative derivatives. And they all kind of have a similar look to the ones that are next to it. So cosines is negative sine of u times u prime. Cotangent's derivative is, we know that cotangent and cosecant will involve each other, just like how tangent and secant will involve each other. And cosecant's derivative is negative cosecant u cotangent u times u prime. Okay. So if I want to find the antiderivative, then I'm really just going backwards from here. So if the derivative of sine is cosine, then the antiderivative of cosine is what? Just sine, right? You're just reading this backwards, right? So if my derivative of sine is cosine, then my antiderivative of cosine is sine. Don't worry about this u prime. That u prime is taken care of by that du. So I'm just reading backwards, right? I'm not really, we're not creating anything new. We're just using the same rules that we have above. So integral of cosine is positive sine. Now we know that antiderivative has a plus c. There is a family of functions that all fit, that all share the same derivative, right? Okay, let me do the easy ones first. If the derivative of tangent is secant squared, then the antiderivative of secant squared is what? Tangent, right?
Plus C.
Plus c, right? So if the derivative of secant is secant tangent, then the antiderivative of secant tangent is secant. So that's this rule here, right? So those are straightforward. Okay. Now these other ones I think are still straightforward. We should just watch out for the negative. So we know that the antiderivative of negative sine must be cosine. So what do you think the antiderivative of sine must be?
Negative cosine.
That's right. So the negative has to go somewhere. So the negative is going to show up in the antiderivative because I'm asking for the positive. So anything that produces a negative derivative will have a negative antiderivative, right? Because that negative has to go somewhere, right? So sine is just simply negative cosine of u plus c. Okay. The antiderivative of cosecant squared u must be what? Negative cotangent. That negative has to go somewhere. So okay. The antiderivative of cosecant cotangent must be negative cosecant. So does that make sense when I say that I don't want you to memorize these? I mean, you can, but there's no need to, especially if you can just have these rules written out in front of you. But I do want to talk about some trouble spots that students experience. Why do you think these gives some students trouble? Yeah, because of the signs, right? Because of the negative, because we're so used to the derivative rules that it feels weird to have this going on, right? Wait, so cosine is a negative sign and sine is a positive cosine. Why is that the case? Because we're going backwards. So just be aware of these two that, but if you have these rules out in front of you, then hopefully you can convince yourself of the correct sign of the signage. So just be aware, these are the ones that are easy to mess up. But it's not hard. We're really just reading, we're just understanding that we're undoing the derivative rules to get to the antiderivatives. Okay. All right, so let's just practice these rules here. What's the antiderivative of 3 secant squared x? That's right. Sorry about these straight marks there. And then those are all positive there. It looks like it's like a negative. Yep, so secant squared is just tangent, so the coefficient is going to hang out in front. X minus 2 cosecant squared x. These are 2 separate rules. X is power rule, so x becomes, yep, 1/2 x squared. And we know that cosecant squared will produce a negative cotangent on its own. There's already a negative here, so 2 negatives cancel out. Yep. Two terms here. This one we can apply the antiderivative rule. This one, what does 1 turn into? It's good. Every power rule for antiderivatives is going to rise in degree, not fall in degree. Was anyone not here yesterday and did not get the addendum packet that I handed out that you guys picked up? Everybody got these. So let's go to these because I forgot to put these, the first and second theorem notes in this packet. If you go to the next page, this is particle motion for antiderivatives. Let me come back to that later. So the addendum packet that you picked up. So this is now this is called first theorem of calculus, which really is just involving bounds. And what we did first was we've been going through power rule. Well, first let me kind of back up. So we know a general derivative is a slope finding function, right? If I find f prime 2x plus 1, that's not the actual slope value. It's a slope formula that I can use to find the actual slope, right? Once I have the formula, I can plug in 3 or 5 or 6, and I can figure out the exact steepness of that curve at that point. So the specific derivative will give me the actual slope at that point. Likewise, the indefinite integral is an area finding formula. So the antiderivative of 2x is just x squared plus c. X squared plus c is not the actual area, but it is an area finding formula that we are going to use to help us find the area or the region between the graph and the x-axis. So the definite integral is the actual area of the region for that interval. So when we involve bounds, then the bounds is going to help us get to a number, and that number will be representing the area. Or how about this, area related value, because negative below the x-axis can be a little different. So it says area, but we haven't quite learned the area formula yet. We'll learn that next unit, but just know that it's area related, but it sometimes may not give you the true area that we're expecting. If the function is continuous on the closed interval, then the function is able to be integrated on that interval. It does not have to be differentiable. As long as it's continuous, it's good enough. So here's the process. we're going to ignore the bounds and just do the antiderivative that we've learned how to do. So we go through power rule, and once we create that antiderivative, then the bounds can come into play, and then we can reach the area of that region. So ignore the bounds, and we're just going to focus on the in-depth interval. We don't have to right now. Yeah, let's just write the problem without the bounds, so we can kind of just focus on the task at hand. So we're going to reach the antiderivative here. So 3x squared becomes what? Yep, 3's cancel out. Okay. 4x becomes
4x squared.
okay. Minus. Okay, so now I'm going to take my antiderivative, x cubed plus 2x squared minus x. Okay, understand that this is now the area finding formula, and now I'm going to involve the bounds. Okay, the way the notation is represented to indicate. Yeah, good question. We're going to leave that plus c out, and we're not going to involve that plus c. We're just going to put the 1 and the 4. Okay. I'll talk a little bit about why that plus c is not needed. So once we have our area finding formula, which is our antiderivative, we're going to plug in our upper and lower bound. The upper bound is going to be first. So the 4 will insert itself into all the x's. Okay. Now that we've taken care of the upper bound, we're going to subtract the lower bound out, minus parentheses, and then the lower bound gets repeated. We repeat the process with the lower bound. $64 plus 32 minus 4 minus 1 plus 2, but minus 1 is just 2. We get 92 minus 2, which is 90. So 90 represents the area between this graph and the x-axis. Now, the reason why plus c is not involved here is because it ends up washing out. So let me show you. Let's say I include that plus c here. So a plus c and minus c will just cancel each other out. So the upper and lower bound is just going to wipe itself out. So we never have to worry about a plus c with area. Now, another important thing is understanding where this formula comes into play, because we essentially apply this formula here. Okay. So this formula says, this is basically first theorem. First theorem says, if I take the antiderivative of my function, it's going to turn into the antiderivative. So that uppercase F means the transformed antiderivative that I went through, and then I plug in the upper and lower bound. Okay. So if this represents the integral from a to b of lowercase f of x dx, then this process here is my uppercase f of b minus uppercase f of a. Okay, does that make sense? So lowercase f means the function that you start with. After you go through the calculus process, that uppercase F indicates that you took the antiderivative. You have an expression that is representing the antiderivative, and you plug in your upper and lower bound, and that will help you achieve the area of that region, of the region under this curve. Okay, so yeah, we mentioned this already. For definite integrals, we don't have to worry about the constant of integration. It will always wash out. Okay, let's try example 2. Definite integral from -2 to 1 of 2x dx. The thing that I think students struggle with sometimes is we read from left to right. So it feels like we have to involve the bounds first, but it's actually backwards. We actually do the bounds last. You're going to take care of the antiderivative before the bounds come into play. So we do not include the -2 and 1 into that 2x dx. So what's the antiderivative of 2x dx?
X squared.
And then once we have our x squared, this is our antiderivative, this is basically our uppercase F. We can plug in our upper and lower bound. What do we get? -3. This feels weird, right? Because we're like, wait, we're talking about area here, so why are we getting a negative value? So I want to just kind of show you that this is what the graph looks like. Okay. We're looking at the region between the graph and the x-axis. Now these are accumulation of y values, right? These are all negative y values. So even though it's area related, this is going to produce a -4 because it's below the x-axis, because these are all negative y values that we're generating. And here, this is giving us an area of 1. It's above the x-axis, so it is +1. So then if we added these together, we get that -3. So if I want to truly find the area, I would have to find the absolute value of each region and add them together. But this is not truly area, but it is what is basically displacement related.
There's such thing as total area.
Yes, and we do have formula for that, but we'll learn that 2 units from now. But there's a formula that will allow for us to always generate a positive value. But here we have an accumulation of y values, which may not always be positive, which is okay. Okay, let me run through a couple of properties, and then I want to talk about the second theorem of calculus, which is very much related to the first theorem. But first, let me run through some properties here. Integral properties. If my bounds are the same, that means I haven't moved. That means I'm starting at A and I haven't created any width for me to find the area. So if my bounds are the same, I basically have no width. If I have no width, I have no area. If I have no area, it's just 0. The integral from A to B is the same as going from B to A and just pulling a negative in front. So if I ever feel like it helps to adjust the bounds, you can always flip the bounds around. Just know that your signs will be opposite than what you start with. So if I want to flip the bounds without changing the value of my problem, I can flip the bounds and just make sure I adjust to that change with a negative in front. The third property, again, sorry for that stray mark there. That's not a negative. That's just a stray mark. If I have a larger region, I can always split that larger region into smaller regions if it helps to see things a little bit more clearly. So for instance, if I have a region that looked like this, if my full region is from A to B, then if it helps, I can split up, and if C is between, if it helps, I can split up into two regions. The area from A to C and from area from C to B. Sometimes it's helpful to break into smaller parts so we can kind of see things more clear. So that's an option. We can always break a larger region into smaller regions. So let's see if we can practice using those properties with the problems below here. We know the region from 0 to 3 gives us an area of 4. We know the region from 3 to 6 gives us an area or a region of value that's -1, which means that it's going to be below the x-axis or a region below the x-axis. So then if I want to find the integral from 0 to 6, I know that 0 to 6 is just the sum of these two regions, right? So this is 4, this is -1. If I add those together, I get what? 3. If I know the integral from 3 to 6 is -1, then the integral from 6 to 3 must be what? +1, right? It's just the same thing, just different signs. My bounds have not moved, so this is always going to be equal to what? 0. Now, number part D is misleading, so I want to point something out. This 3 is not a +3. This is under the umbrella of the integral. So we really help us see things more clearly. It helps to treat them like two separate problems. So this one has f of x in it. We could definitely use the property to help us fill this in. But this is a standalone problem. We don't use properties. We use what to go through this? Power rule. Yeah. So this we do power rule. This one we can do property. So I pulled the -5 out to show that I can just make a substitution with this. The integral from 3 to 6 is simply just going to be -1. So that's -5 times -1. And this, I can step to the side and go through its own process, right? Let's find the antiderivative first. 3 becomes what?
3x.
3x. And then we can evaluate the bounds. Upper bound first. So we get -5 times -1 plus 9 is 14.
That's the same thing as just in the original part. Is it just the same thing as multiplying the function out by 5, distributing 5?
Yes. Yeah. So example 4 here, we see a variation of first theorem. Okay, it says that if this is equal to 10 and f of 8 equals 6, what's f of 3? Now, this is another variation of first theorem. If I start with lowercase f, I can make it turn into uppercase f to represent the antiderivative. But if I start with f prime, what's the antiderivative of f prime? Just what?
F of x.
Just f of x. So this is really just an application of first theorem, right? I know that integral of f prime will just turn into f of b minus f of a. So if I can spell that relationship out, I can kind of see a little bit more of what's involved here. So the integral from 3 to 8 of f prime, without looking at that 10, I can spell that out to be what? This turns into, f prime turns into f. Yep, f of, well, f of
Wait,
8, upper bound, minus f of 3. So this is my equation that I know is true because of first theorem. And now I can fill in the pieces, right? I know this is 10. I know f of 8 is 6, and then I can just solve for f of 3. Now it's just a simple algebraic problem to isolate f of 3. F of 3 it's just equal to 6 minus 10, which is -4. Okay, I got to try to squeeze in second theorem before bell rings. So if you guys can turn to turn to the next page, 6.3b. Okay, second theorem is a shortcut of derivative and integrals. Okay. So, but I realized in the past that it's hard for students to appreciate the shortcut without fully seeing what the shortcut is, what's it actually doing. So let's just try example 1 here. So example 1 is a two-step process. Okay, we're going to take the antiderivative. We're going to plug in the upper and lower bounds. And then after all that is said and done, we're going to turn around and find the derivative. Okay. The big picture here is that we're doing something and then we're undoing it. Right? And the shortcut is, how can we get to the answer without having to go through that full process if we know that we're just going to undo it? But it's helpful to see it from beginning to end. So let's just focus on the antiderivative. So 2t minus 3 dt. Remember, we're dealing in terms of t variable here. So what's the integral of 2t minus 3?
Squared minus 3x.
Okay. Yeah, t, yep. Sorry, 2t squared over. Yeah, which is just t squared. Yeah, I'm going to write that the full thing and I'll clean it up. Okay, now that you have your general antiderivative, you can plug in your upper and lower bounds. So x squared and 1. Upper bound into t first. Minus, then the lower bound. Okay, let's do some cleanup here. I get x to the 4th minus 3x minus a -2, so plus 2.
Should it be 3x squared?
Oh, sorry, 3x squared. Thank you. So now that we've taken care of the bracketed portion, now we're going to turn around and find the derivative. What's the derivative? Mm-hmm. Mm-hmm. And that's it, right? Okay. So what is the shortcut? I know it may not quite feel like a shortcut because this is not a difficult process right now. But if this was a messier problem, imagine having to go through a messier process and then find the derivative. It's doing a lot of things or doing something and then undoing it. So this is what first theorem tells us, or second theorem tells us. It tells us that if I'm pairing two opposite operations onto the same function, we can do this shortcut. So the shortcut says, all I need to do is plug the upper bound into the original function, because I know these two operations are essentially going to cancel each other out. But there is going to be some effect of the upper bound with the derivative. So I multiply the upper bound by p prime. It's going to feel a little bit like chain rule-ish, but it's really undoing these processes. So I want to kind of show that process for this problem. Okay, so I have two operations undoing each other. First thing I do is I just plug the upper bound into the function. I'm not doing anything with it. I'm just plugging it in. Normally, you would never do this, right? Because we require the antiderivative, but we know that we're going to undo the process. Multiply it by the upper bound's derivative. What's upper bound's derivative? Distribute that through, we get 4x cubed minus 6x. the same thing as if we were to go through it the long way. Now, notice that we have nothing to do with the upper lower bound. That lower bound is a constant. That constant drops out because the derivative is going to force that constant to go away. So we never have to worry about the lower bound if it's a constant. Okay, we'll do more review of this, but at least you have enough knowledge to start the homework. Okay, so I'm going to check 6.3 tomorrow. Come get your phones.
See you tomorrow. Page 5. I see that. From the head. Yeah, have you go over there? Very good, thank you.
Yeah.
Bye, thank you.
Yeah, that's also a.